Hi, in this video, we're going to take a look at ensemble models and supervised learning. Okay, so in the videos, I've been talking about all these different model structures to use a model to make a prediction. Now what we want to do, we want to take multiple models and combine them so that I get a better overall model than I would with one single model. All right, so professionally, I typically use this that I'll build like a whole series of models, and then of all of which are different model structures. And then I'll take my top three and then combine them in some manner. Now, something that you might want to do if you're real eager after you've built all those different models, let's say you built 20 different models. Well, you know what? When we first get into data mining, supervised learning, it's real tempting to try and get the best model possible by using all 20 of those models. Don't do that, my friend. What you want to do is only take your best, because your weaker models are going to pollute and drag down the stronger models. So only take your strong ones. And that's my advice to you. I personally go with three of different model structures, combine them in some manner to get a better output. Now, when you start nuancing things, you start like really digging into your models, it's typical for your ensemble model to not perform as well as the best model that is in there. But remember that when we do an ensemble model, we usually improve some other aspects, not just the accuracy, but we also reduce the variance and the bias of our models. And we can also improve our predictions on the areas that my best models has like weaker performance. All right, so when you hear the ensemble, that's where we combine models built on the same target variable to get us a better overall model. Oh, and we can also do this in several different ways. We can use predictions together in like an average, or we could use predictions together in like a voting, or predictions together as predictors in another model, or we could actually use predictions as a feature engineering technique for another model that we built. We have lots of options. All right, so typically when we're doing ensemble modeling, we're trying to decrease variance and decrease bias and just improve our prediction. So we're trying to improve our model every way we can, honestly. And we can do this for both for classification and regression problems. All right, so what we want to do, we want to aggregate predictions from multiple models to get the strengths of each individual one. So different model structures are going to pick up different features in my data. And what I want to do, my goal is to go and when this model is strong, let this one speak loudly. When this model is strong, let it speak loudly. And so that way, when I combine them, I get the best result possible. All right, so let's go ahead and start working on some examples. I'm going to set my workspace as I always do, suppress digits on the output, avoid scientific notation, suppress warnings I don't care about, make sure that my workspace is clear, and I'm going to be doing piping. All right, so I'm going to be using I'll be using the house prices dataset and the mushroom dataset, both of which are from Kaggle. Here are the predictors I'm going to use for the house prices. I keep that in a vector called V house prices. V stands for vector. Now, different model structures require, or not require, but it's best practice with a lot of model structures. I have, standardized ranges for my predictor variables. So I'm going to go ahead and rescale the predictor variables. Also, you'll notice that in this part here, I'm setting up my train test validation splits. Now on the mushroom data sets, I'm actually going to get rid of my best predictor variables. All right, so it works out that how I did my data prep back in, several weeks ago, that odor is just like a really, really powerful predictor variable on the way that I did my data prep. And so if I include that, the model is going to be so accurate that I won't be able to show you the power of doing an ensemble model technique. I need some errors in there for there to be like a meaningful aspect. So I'm only going to use these two predictor variables in the modeling. At work, I wouldn't be doing this. In real life modeling, I wouldn't be suppressing things like this, but I'm doing feature selection to get a worse model so that it's meaningful to show you the ensemble results. All right, so let's go ahead and fit some regression models. So what I'm going to do, I'm going to use the train function in the caret package to do this pretty quick and easy for myself. And I'm going to do support vector machines, stochastic gradient boosting, ranger, classic linear regression, and k-nearest neighbors. And you'll notice that all of those are different model structures. Stochastic gradient boosting and ranger are both tree models, but they have different approaches to building the forest. So I still consider them separate for this purpose. And I'm going to go through and I'm going to build my models on the train validation split data. So remember that the train package, the caret package train function automatically handles bootstrapping of training and validation for you. And so because of that, I'm putting my training and my validation set together for that bootstrap overall. So what's actually training, what's actually validation on parameter tuning is not actually the way that we intend it. But for this purpose, it doesn't really matter. And so here I have the prices, which in the previous video, I did a Box-Cox transformation to improve the distribution. And so this will go through, and I'm setting it up so that each of these different model structures are getting parameter tuned inside the train function. And I'm doing this in the lapply function. And think of this as a slicker version of a for loop. It's faster than a for loop in R, and I don't have to worry about the iterations. It just takes care of everything for me. All right, so now I built, what was it, 5 different models? Yeah, I built 5 different models. If I was doing an ensemble model at work, honestly, I would limit it to my best 3, unless I had like a close tie or there really wasn't like a really good model at all. But in most situations, I limit it to my top 3. All right, so I want to take a look at each of the individual models just to see how things, turned out. And so let's go ahead and take the root mean squared error. So here we can see how ranger, support vector machines, stochastic gradient boosting, linear regression, and k-nearest neighbor turned out. Here's the training, validation, and test statistics. All right, so when I look at the test statistics, these are all pretty tight. We can see the k-nearest neighbor is the weakest. Then, here we have our validation. And so under validation, we see that ranger did the best. But remember, we had, that was that labeling. I didn't do the full proper thing. I went ahead and let I let train handle the bootstrapping for me. And so here I'm interpreting this as being optimistic, but here things are pretty tight. And one thing I'm worried about is looking at the difference between ranger and test. Now, it looks like ranger is doing pretty well. It's a strong model in test accuracy, but I am worried that I have some overfitting going on. Sometimes I'll have like overfitting and an overfit model slightly and still have that be my best test set model. That will happen. It's just something to be mindful of as we proceed. If I see indications that ranger is showing other signs of overfitting, I'm going to have to pull back off of that. All right, so we have a bunch of different ways for us to combine our models. We have 5 different models, and the first way to go through and just combine them for regression or for the purpose of modeling probabilities of a 2-level result, such as logistic regression, is to go ahead and just average them straight. Just take the 5 models, give each model the same weight, and then take an average. All right, and that's by far the simplest way. So I'm going to go ahead and do that. I'm going to use the row means function, easy peasy lemon squeezy, where I'm going to get the predicted values, which I put into this data frame, and I'm going to select only the models I built. and I just go ahead and do the row means function. Boom, easy peasy, lemon squeezy. We'll look at it later, the exact values. Now, if I can do an average, I can also do a weighted average. So let's say that I have all these different models and I have more faith in one than I have in the others. Okay, well, then what I can do is I can put more emphasis on the models I have more faith in. All right, so then, I just need to choose what those weights are. I just basically just made something up real quick and easy like this. And, it could be a random number, could be anything for this purpose for the example. But I just decided here I'm saying that K nearest neighbor is highest priority and Ranger's lowest priority, or support vector machines is the lowest priority. And so just going through, doing a weighted mean as simple as possible to get another ensemble model approach. Now, another thing that we can do is that after I get those predicted values from those 5 submodels, I could take those 5 submodels and treat those as the predictions as feature engineering for other models. So I could take the predictions on scored value, take those that I get, those 5, as predictor variables in another model. And I'm going to do this in 2 different ways. I'm going to do one with bagging with the Ranger package, and the other one I'm going to do boosts with stochastic gradient boosting. All right. And so you'll notice that when I go through and do this Ranger one, the only predictor variables I have are the ones that are from the actual predictions. And so I have submodels making predictions, and I take those predictions, put them into like the overall ensemble model. Is how I'm approaching this. All right, and so here I'm using Ranger for the bagging. Here I'm using gradient boosting model for boosting. And now let's go ahead and compare our models. So now be ready for it to work out that our ensemble models will not be our best models in terms of any one statistic. It's kind of like an overall improvement, but typically if I have my best model for prediction and I add another one into it with an ensemble, the ensemble model is going to be in between those two for any statistic that more than likely any statistic that I'm going to build in most cases. And that's going to be the case here. So I'm going to go through, I just want to set it up so I have an idea of what's going on. All right, so let's go ahead and do our train statistic, our validation statistic, our test statistic. And so we've got, so I've got this sorted by validation. And by validation, we can see that bagging is the best and Ranger is second best. So we have ensemble, not ensemble, ensemble, not ensemble, ensemble, not ensemble, ensemble, and then the last 2 are regular models also. So you can see that it ends up that any metric that I'm going to be working on, more than likely the ensemble is not going to be the top performer. Whatever was the top performer before I combined models, that's probably going to be the top performer after I get the ensemble version also. And so here we can see that we do have an improvement on the test statistic off of this. So the test statistic is improved. It's not a huge improvement, but it is better than what I had on individual models. All right, so now something that is important to understand is that when I'm doing this, my predictions are going to be highly, highly correlated with each other. So I built 5 different models on the same target variable with the same predictor variables. Those 5 models are all trying to do the same thing. They're just approaching it in different manners. And because of that, they're all going to be highly correlated with each other. And so something I might want to know, I might want to understand is to check to see what's the difference between these. Now, to really answer that question, you have to honestly start going like row by row, individual observations to go through and understand what's going on with the models in a more nuanced manner. A way that we can at least get through the first layer, get a coarser understanding that takes less time and it's a little bit easier to understand, is to go ahead and use correlation analysis and principal component analysis. All right, so here I'm going to run correlation analysis, and I didn't bother with splitting it. I really should have, but here you can see that my predictions are really, really, really highly correlated with each other. It's near perfect correlation. It's not exact. There is some disagreement between my models. If I had perfect agreement between two models, I would have a 1 for the correlation. Now, another way that I can analyze it, and this is a little bit deeper, is for me to go ahead and use principal component analysis or factor analysis and check to see what are the loadings, what are the coefficients in the factor analysis that I've got going on. Typically, when you do this, your first principal component or your first factor is going to be a representative of the entire model. And approximately speaking, all of the loadings will have the same values, approximately. Or all the coefficients in the factor analysis will be the same. And so let's take a look at this. All right, so here I've got my standard deviations for my principal component analysis on those 5 models. And I'm running this on the predictions. And you can see that that first component is by far the biggest for standard deviation. The rest of them aren't even added together. The other 4 don't account for it. So really, if I was thinking about this in higher dimensional space, in 5-dimensional space, this would end up being a very, very, very long pointed javelin shape of dots in higher dimensional space. And so our prediction value, to a large extent, is going to be like where along that javelin shape is the individual value, where along that length. So now check out the loadings. Here you'll notice that these loadings are all approximately the same. So this gives us an indication that the models are all relatively contributing, the same amount to the principal components. Now, one thing about this type of analysis is that this principal component, I could actually use the first principal component, second principal component, and so on in this situation as feature engineering, by the way. I choose to not do that because it's been proposed as being very powerful, but when I've tried it, I've never seen an increase over performance over just going with the raw values going in. Now, here's something that is interesting. Check out the second principal component. You'll notice that the second principal component we have a negative value for linear regression. We have a negative value for k nearest neighbors. Okay. And then we have positive value specifically for stochastic gradient boosting, and positive value for the Ranger package for random forest. And then this is a rather small value. So just conceptually, I'm going to go ahead and ignore that. But what this is telling me is that Ranger and stochastic gradient boosting along the second principal component are giving the same information, while linear regression and k nearest neighbors are giving different information. And the 2 that are going to be the most different from each other, I would say, is k nearest neighbors and stochastic gradient boosting. So if I'm looking for diversity in my predictions, I'm going to first look for extreme opposites on the second principal component. And so that k nearest neighbors is the largest negative value. Stochastic gradient boosting is the largest positive value. So that's showing me that the 2 that are the most different are going to be those 2 models. And then we work inward towards 0 in terms of magnitude when we analyze further from this factor analysis point of view. Now, we can also analyze component 3, 4, and 5 in a similar manner. But generally, component 2 is going to be the one that we look to the most that accounts for the most variance, the most spread of the data in higher dimensional space. But here it would be worth considering 3, since these are so close to each other. And that's not much of a difference. And so when I look here, component 3, I've got a negative 0.78, and then I have a positive 0.67. So this is reaffirming that Ranger and linear regression are giving me different information in my model. And so look at the large values, look at the most extreme ones, and try to like group them up and contrast them to figure out where are the similarities and the differences occurring. All right, so another thing that we want from our ensemble models is to have a reduction in variance. And so if I'm taking a mean, I'm going to have a reduction in variance more than likely. And so this is a nice aspect. So I can improve my predictions and I can reduce the variance of my predictions at the same time. So from a statistician point of view, this is a win-win. Now, ensemble models, this is great, but remember that ensemble models, I'm using multiple models. Every single model I use, every single feature that I use in this is an opportunity for something to go wrong down the road when my models are in production. And typically, we don't bother with ensemble models if we don't have to. The reason why I don't use them is just because down the road, there's just more opportunities for something to fail, and I want things to be robust. I want it to be reliable. I don't want there to be issues down the road that, oh, something failed and either I have to fix it or my reputation gets damaged because, oh, Aaron's model didn't run in production this morning. You have to go fix that headache for us. And so I typically use ensemble models when it's a one-shot deal, but if it's for production, I avoid them. Actually, I've avoided them every time for actual true production models. All right, so let's go ahead and take a look. I split out, so I've done 2 things. I took a look at the 90% observation range by binning the data. So I went through and I binned by the target variable. So I took the target variable and I binned it into 10 subgroups. At work, I typically use 20 subgroups, Vigentile plots, but I felt like Vigentile plots got too complicated for the visualization here, so I went to 10. And so I'm going to get a 90% observation interval for each of those bins, and I'm binning by the target variable, not the predicted value. That's important. And I went ahead and did this interval for training, test, and validation, and we can see what the variance is, like a visual representation of the variance across. And so we can see what looks like linear regression has the widest overall, while let's see here on training, Ranger is tightest, while on the test sets they're all pretty close. Maybe support vector machines is the tightest. Now, this is all the original models, and we can see kind of a gap going on. This is a pretty wide channel. If I consider the ensemble models, it tightens up, especially in the validation and train. If you go through and you actually like really nuance this, you'll see that there is a reduction in that spread. Going on to just improve the variance aspect. It's not a huge difference. It's not like between night and day, but it is an improvement. And as an improvement, this is a good tool to have in our tool belt. Now I'm going to use the same bins, and I'm going to go through and compute interquartile range. I didn't use standard deviation since I just did 90% observation on interval. I thought that was close enough. But if I do interquartile range, here I can see by bar plot what the interquartile range is on each of those bins. The bins are set up by the target variable, and I'm going from least to most average interquartile range. So we can see that the Ranger has the least, then the original data, then bagging. So Ranger actually has less spread than the original data does. That's interesting. Then we have bagging. So we can see that bagging does a pretty good job on reducing, the spread of the predictions. And then we go through this list here. It's interesting to see that boosting has the biggest spread. It has the most spread out predictions within the bins. And specifically, we can see that boosting is having a harder time on the extreme ends than the other models. And so this plot is good for telling me that if I was going to go with that boosting ensemble model, I would have less faith in what's going on at the extremes than I would have in the middle. We can see this pretty low, pretty tight in the middle, but far out, that's way more spread out than the rest. All right, so we've talked about regression models for ensembles. Now let's talk about classification. Okay, so in classification, if I have modeled probabilities, well, if I have numeric values from probabilities, I have all of the techniques that I just talked about for regression. And we have those. I'm only going to show the mean technique here just because I'm lazy. But all those different techniques that I showed a moment ago, we can apply those with the probabilities that we get. But we also have other techniques. We have voting, and we have like disagreement situation. And I don't have a good name for the disagreement one, but I'll explain it in a little bit. All right, so if I have probabilities or modeled probabilities for the likelihood of being in a class, or I have zeros and ones, I can treat those as numeric values and use all the techniques that I've used before. So let's go ahead and look at one where I'm going to use row means. So what I'm going to do, I'm going to go through and I'm going to take the different methods I'm going to have. I'm going to build 5 different models. And I'm going to, now here, when I go through and do this, I need to set the type to the probability of this. Now, to be able to get support vector machines to give me what I want, I need to run it in a particular way. So I'm doing that here. And so now I'm going to do a bubble plot to take a look at visually what is the accuracy of my models. All right, so I've got stochastic gradient boosting, GLM net, K nearest neighbors, random forest, and support vector machines. And you'll notice that in terms of accuracy, so I sorted these models by their accuracy. They're not, that's not, actually, I need to double check something. Yeah, so I am ordering by accuracy, by the mean absolute error. And so we can see that the mean in terms of accuracy is not my best model, but I can expect it to reduce variance also for me. So that's an advantage. I might want to do, just GBM or GLM net or K nearest neighbors. So here, expect the mean to be somewhere in the middle of your models in terms of accuracy. And so if I was to drop support vector machines and drop random forest, I could expect the mean to actually be among these 3, and I could improve my predictions overall. And you'll notice I'm getting more diversity in the output of my model when I combine like this. Now, another technique we can do is voting, where here we go through, and if I have multiple models, I can have them vote for what level they want it to be. So previously we took the probabilities and we combined the probabilities. Now we're doing like an all or nothing. And so if a model gave a model probability of 0.51 or 1, that results being the same level if I'm doing like logistic regression. And so I prefer to work with the probabilities and then move to the level, but that's not always possible. Some model structures. Now, all model structures give us probabilities out. And so in that situation, maybe I'll just take all my models, I'll have them predict the level of each observation, and then for each observation, I'll have the different models basically vote to see what level do I assign, what is the classification. And so here you can see that I've made a prediction for each observation using the different models. All right. And so, we've got all of these, and you can see that, we've got overall some pretty good agreement. It looks like there's something weird going on with k nearest neighbors, but we can also see that the true value is P and only k nearest neighbor got right. Now that's kind of interesting. Here's P and only k nearest neighbors got it right. So, it might be worth it to keep, a variety of models going in. And so now let's go ahead and plot it. And so in this situation, I ordered all my models by their performance. And so k nearest neighbors is the worst performing model. Voting is the best. And so you can see that my ensemble model ended up giving me on average the best. Now I took the average across training, validation, and test, by the way, that way I could sort it for this visualization. But I don't see any issues of overfitting, and things are looking pretty good. So I like the voting result that I got out. Now another way that I could go about doing classification, let's say I've got 3 models. I have my strongest model, second strongest, and then my third. All other models I built, I'm throwing away. Now, if my first and second best models agree with each other, I should use those predictions, right? So if they agree, I'm just going to go ahead and go with it. Now, what do we do when my best 2 models disagree? Well, what I propose is that you take your first best model and your third best model when you have that disagreement going on. And if the first and third agree, then you go with a prediction. If it still doesn't work out, then you go with what 3 and 2 agree on as the level. And this gets more complicated when I have more than 2 levels, by the way. So if I had like a 13 level classification problem, this can get pretty nuanced. I find that this technique works very well the more levels I have to work with. So imagine I have 13 levels for classification. Well, I have 13 levels, then there are 12 ways to be wrong. If my best model and my second best model agree, then more than likely, that's the best that I can pull out of this data. And so all those cases, I should just agree with it and go with it. Now, when they disagree, remember, if I have 13 different levels, it's possible that both of them got it wrong. And so then it gets more tricky, gets more nuanced. And so what I'm trying to do, I'm trying to find where do I have agreement in a situation. So of the ones that first and second disagree, I'll take of those when first and third agree, take those values. Now, of the ones that still haven't been classified, check to see when second and third agree. And I can keep on doing this with more and more models if I want. But for me personally, after I get through second and third agreements, I just go with the first model that I have, my best model. Now, I've used this in the past to go in and spot check individual records, because if of my 3 models there's no agreement at all, then that's a sign that there's a problem with my modeling and or the observation. And that's a short enough list by that point that I can go in and start digging into and picking at what's going on. Specifically, I've done this for bags of word models. And so I've just had a situation where the text analytics just misclassified some things. I read as a human being what the values were, and I assigned the level correctly to improve my overall model. Now, when you select your models for doing ensembles, if I built 200 different models, I'm not going to use all of them in an ensemble. First and foremost, I'm only going to use my parameter tuned models, and I'm only going to select my best ones. Maybe 5, maybe 3, 4, but not a whole heck of a lot, because having weaker models included will pull down your stronger models. We want to only have a strong result. And also, if I'm doing this, we have a huge amount of correlation and agreement with our models if they're even remotely accurate. And because of that, I have highly correlated predictor variables in the ensemble, which it means I have a huge risk of overfitting. We have to be very careful when we do this. Be cautious, be careful when you're doing ensemble models. You can overfit very easily. All right, well, homework. Your homework is to go and build 3 or more individual models on the same target variable and build an ensemble model and just see what happens, get experience with it. And that's all I've got for you. Life is short. Do math.